we started talking about simple harmonic motion. We said there's lots of periodic motion, but the simple harmonic motion is a particular type of motion. And what was it we said is the distinguishing, anybody remember, what's the distinguishing feature of simple harmonic motion? Anybody? No? That is a feature. But what this is a repetitive motion, right? But it's not simple harmonic motion. What's the distinguishing feature?
Hooke's law? Hooke's law?
Yeah, Hooke's law. Right. The idea of the restoring force. Okay. And so we said in Hooke's law we have the force is minus kx, and you know, when we said that when we displace something with the spring, right, the displacement is to the right, but the spring force is to the left. Okay, so that in Hooke's law we have that relationship, and that is what creates simple harmonic motion. Now we pointed out that they're referring to a horizontal oscillation, but we're going to show it as a vertical oscillation. Now, I think you can just set that and just leave it. It'll be fine. We don't need perfection necessarily. Okay. So we talked about, there's a lot of definitions here, but none of them really that complicated. If we just look at them, so the idea of period is, if you just think for a second what a period is, you know, it's time. How long for one cycle or one oscillation or one revolution? And then we have the inverse of the frequency, and then we talk about the displacement. So this is the definition. It's a cosine curve that he used. This is the amplitude. This we call the angular frequency, and the time, and then the phase constant. Okay. So here's a picture of an oscillation, and we can make it into a sine wave. And there's our displacement cosine function. And here is the equation. Where the light's a little dim. I guess that bulb was going out. Anyway, does it seem dim to you? Yeah. It's a little bit dim. It's dimmer than the other room, but you know. I have to turn that light up. Anyway, here it defines the parameters. The phase constant, this one is confusing a little bit to people. And we said, if we look at these graphs down here, that this bottom one shows us what the phase constant is. It just means that the graph shifted. So this has a phase constant of minus pi over 2. Negative means it shifted to the right. Okay. So then we looked at the equation for displacement, and we realized that if I want a velocity, the velocity is the first derivative of x, right? So we just take the first derivative, very straightforward, and we have an equation for velocity, and then we take the second derivative, we have an equation for acceleration. And those equations then are describing the position, the time, the velocity, and the acceleration of our simple harmonic motion. Now, okay, so we're going to look at different aspects. So the first thing we look at is the force. And of course we know that force is mass times acceleration. And we can substitute for acceleration. And so this is in terms of x, and they're not showing the cosine function, but that's fine. But Newton's second law is mass times acceleration, and this is minus omega squared x. And if we substitute for that, we get this expression, but we notice here, if we rearrange this as minus m omega squared x, we have our force law, which is minus kx, so k becomes m omega squared. In other words, in the linear, our force constant in simple harmonic motion is mass times omega squared. And we can solve for the angular frequency, which they do below, and it turns out to be k over m. Now, okay, so k is our spring constant, and the mass, and we see the angular frequency is simply related to the mass and the spring constant. Now, we can get the period from that because we know that omega is 2 pi times the frequency, which is the square multiplied by k over m, and this is 2 pi over the period square root of k over m, so you can see that I can solve for the period. It turns out to be 2 pi over omega. And I did that wrong. Put this wrong. I don't know what I was even thinking. You gotta watch me. I'm liable to do anything here. This is omega.
Yes.
Thank you. Point that out when I make mistakes of that. Point that out if I make a mistake. This is 2 pi times the frequency over here, which is square root of k over m. This becomes 2 pi over t square root of k over m, and then when you solve for t, you get this expression, right? Yeah, t on one side, 2 pi m over k. So a different way to, that's usually the way we think about it, because the period is more measurable for an oscillation. The period is pretty obvious, so usually you see it, or oftentimes you see it in this form. Okay, but the point is we can solve for the period that turns out to depend upon the mass and k. Now, what's interesting about that then, notice there's no amplitude here. We don't. It doesn't matter what the amplitude is. We can have a large amplitude or a small amplitude, we still have the same period. It just depends upon the mass and the spring constant. Okay. Well, let's take a look at this checkpoint 3 in a sample problem. So if we look at this for just a second, what do they say? Which of the following relationships between the force on a particle and the particle position gives simple harmonic motion? So which of these will give simple harmonic motion? How about this one? Then, how about that? Well, I get simple harmonic motion out of this force. Yeah, because it's K here is a constant -5, right? Okay, how about this one? No, that's an x squared, this one.
Yes. No.
No, why no?
Always don't proper negative.
No negative sign.
Yeah, it's not negative. So what this says is, this is a little tricky. As you move to as you increase x, the force gets bigger. It's not a restoring force, right? It gets larger. And here, another one, which is a no. Okay. So, very specific thing. Now, of course, we pointed out that if we have simple harmonic motion, we can use mathematics to help us analyze it. So let's look at this little problem here, which shows us some different ways, or different analysis of simple harmonic motion. Try to get this the right size. How can you get rid of this thing? How can I get rid of it? Okay. sorry. No, there it is. Okay, so what is it? You've got a block and a mass of 680, and it's fastened to a spring with a spring constant, okay? So we got a mass, and it's on a spring, and I guess it's oscillating, and K is 65, and X is 11 centimeters. So they pull this out to 11 centimeters. Okay, and equilibrium position is 0. On a frictionless surface and it's released, what are the angular frequency, the frequency, and the period of the resulting motion? Well, we have our equations that we've derived. So here's the angular frequency is K over M. We know K, we know M. Simple enough. And the answer is in radians per second. And remember that omega is the radian frequency. And then F is 2 pi times the frequency. Excuse me. Omega is 2 pi times the frequency. So we can solve for F here. It turns out to be about 1.6 hertz. The period 1 over F. Okay, so just showing you some problems. Now the test, I'll give you some questions just like this, just some basic parameters, right? So maybe you want to make a sheet for this, or I can give you one. Or you probably want to make your own. Probably want to make your own, or be aware of what's in the textbook there in the back. You know, if you have a handy sheet, I think it's worthwhile to make your own sheet of critical equations. I don't think it'll take that long for this chapter. You know, just these basic equations. Or remember to use that back pages as a guide. Huh? Okay. Now, so with no friction, then here's the question: what is the amplitude of the oscillation? Now, the amplitude then is x sub m, and so let's see. The amplitude is just simply 11 centimeters because when we stretch the spring, we know that it's not suddenly going to go to a larger amplitude. What did I do with my spring? It's not suddenly going to. If anything, in reality, it'll get smaller, right? It's easier to do this vertically. So we have some amplitude right above the equilibrium point. Remember, if the amplitude is above the equilibrium point, okay, or below it. But so that's the amplitude. What's the next one? What's the maximum speed of the oscillating block, and where's the block when it has this speed? So then what V max? So here is the equation for V max. What's the equation for the velocity? The velocity is minus omega x max sine omega t plus phi. And when will this be a maximum? When will that be a maximum?
When we call what?
Yeah, when the sine function, that's right. When the sine function is 1, everything else is fixed, right? The amplitude is fixed, and so is the frequency for a given situation, right? But this is the oscillating term. This is the term that oscillates, the sine function. So this will be a maximum when the sine is 1, and so we get v equal minus omega x max. Okay. So we know x max, which we said was 0.11 meters or 11 centimeters, and then we have omega. We get 1.1 meters per second. Simple enough, huh? Now, so where is it? That is well, if we think about the motion, huh? If we think about the motion, of something oscillating, right? Here's it's oscillating. Out here, its velocity is 0, right? The other side 0, so our maximum velocity in the center. Okay, so you just need to think about a little bit there, and you get the maximum velocity. So you know maximum displacement, maximum velocity, and maximum acceleration is a little tricky. We said that occurs out here at maximum displacement, where we go from moving one way to the other. That's our maximum acceleration. Okay. What's the magnitude of the maximum acceleration? Again, we have an equation, acceleration minus omega squared x max cosine of our argument, and there again, maximum will be when cosine is 1, huh? Okay, so we get the maximum acceleration of omega squared m, and they just drop the negative because they want the magnitude, right? So we know omega, solve for that, we get 11 meters per second squared. What's the last question there? What is the phase constant for the motion? That's a little trickier, but at time t is equal to 0, right? That's when the phase constant, in other words, where does this curve begin for x max? You know, does it begin just like the cosine, or is it shifted? You know, is it shifted somehow? You know, and so if we let t equal to 0, then if we let t equal to 0, we know that that's equal to x max, because that was the initial conditions, and that gives us a cosine of phi equal to 1, right? We have this, where's our equation? X equal x max cosine omega t plus phi. So if this goes to 0, we just have cosine phi, and the value of this is 1, right? So the cosine of phi is equal to 1, and that means the phi is 0. Okay. Carlos, are we good? Okay. Simple enough. All right. What's the last one? What's the displacement function for the spring block system? So here they substitute the known constants, and so we said for this particular problem then, x max is 0.11, omega 9.8, that's 0. Here's the equation. Here's the equation that describes that particular set of conditions. 0.1, 9.8. That's in radians. That always throws you off a little bit, right? Radians. Okay. So you're used to thinking in terms of degrees, not for a cosine function. Okay. So what are they doing here? So here's a different one. At t equals 0, the displacement in a linear oscillation is minus 8.5. The velocity at time 0 is minus 9.8. Its acceleration is 47. What's the angular frequency of this system? So they've given us 3 equations here, and they're looking for the angular frequency, which is omega, and this is a little bit trickier. So these are our initial conditions, and we're looking for omega, so they divide acceleration by x. Oh, I see. Looking at the equation,